And welcome back to Calculus 2, section 8.6, alternating series. This is the 10th and final test in this chapter. There are more than 10 tests. Those of you interested in mathematics will go on with analysis courses and you will find all these other tests that are available in advanced calculus and so on. These are the 10 basic tests that we know. So alternating series is the last one, and the form for alternating series will be, it starts anywhere, 1, 0, 5. It's going to have -1 to the k, and then some ak following that. So you are going to recognize alternating series easily, because it will have this -1 to the k, or k plus 1, or k minus 1, whatever. Why is it alternating? What this -1 to the k does is it makes points jump on the other side of the number line, right? So you will have a situation, let's say, like this. Right? That's what it does. Rather than having all points above or below. So these can converge or diverge, right? Most likely you are looking at the one that it's convergent. As you add all of these numbers, they add to a finite value. Divergent one, obviously, it's going to probably fan out like this, right? So that will definitely be divergent as you, right? Keep adding, they add more and more, so they add to infinity. So we can still have convergence or divergence. Now, there is a pathway for this, and I would strongly recommend you draw this on the sheet. Well, first do it in the notes to practice, and then maybe on the back of the sheet or on the side somewhere, because alternating series is in the middle somewhere on your sheet. It is a structured procedure, because now we are going to have two different types of convergence. We're going to have the absolute convergence and conditional convergence, and then we'll have divergence. So there will be three different possibilities in this case. Now, this absolute convergence corresponds to convergence as you know and love it so far. So far you had convergent to divergent. That convergence was absolute convergence. But now you're adding a new aspect, which is conditional convergence, and we'll see those problems as well. So this is how it works. You are starting from a series that has alternating term in it, and you immediately extract AK. So that's what you extract. So you strip off this alternating term, right? Take it away, and you're just looking at AK. Now, you test two things. You test decreasing, and you test if the limit AK is 0. As k goes to infinity, obviously. So this is the procedure. You isolate AK, and then you test if AK is decreasing and if AK limit is 0. If the answer is no to any, you have divergence and you are done. But if answer is yes, yes to both, in that case, you will have to test summation of AK, and I will put here in parentheses using any, not any, using appropriate. Appropriate is the word. Test, meaning you have already those 9 tests. that you know. It might be integral, it might be p-series, it might be geometric, telescoping, whatever. And then if it converges, you will have absolute convergence, and if it diverges, you will have conditional convergence. So this is the like a tree diagram, pathway, algorithm, whatever you want to call it. So you're starting with -1, series -1 to the k, ak. You isolate ak. You check these two conditions. If any of the two conditions fails, you are in divergent track, you're done. But if they both pass, you are in a convergent track. And then you check summation ak without alternating piece. If that one converges, you have absolute convergence. If that's a divergence, you have conditional convergence. Now, what is this business of conditional convergence? Well, observe that you are on the convergent track just because these two conditions held, right? So since these conditions hold, you're on convergence track, so you have to get convergence on both. This one over here, diverging, means that you are getting conditional convergence. What condition? The series converges if it has alternating piece in it, and diverges if it doesn't. So obviously conditional convergence. It just makes so much sense when you see it that way. So the original problem is on a convergent track because it passed these two. So the original problem, which does have -1 to the k, converges because it passed these two. Without -1 to the k, if it diverges, we call that particular problem conditional convergent, right? Because if -1 is there, it converges. If -1 is not there, it diverges. So that's why it's called conditional convergence. And we'll see an example for that, the best example in the galaxy. We'll see that. Now, I need to make sure you also have this piece. I'm going to write this in purple because that's our favorite color. So alternating term is this -1 to the k, or k -1, k plus 1, whatever you come up with there. But there is also alternating term in disguise. And that one is cosine n pi. That's a very fancy way to write -1 to the n. Maybe I should call it k. Let's call it k pi and then keep k. All right, everywhere. So what's cosine of pi? -1. And cosine of 2 pi? 1. And 3 pi? -1, right? So this is a very sneaky way of getting the, what's sine of k pi? 0, 0, 0, 0, 0, right? You can do also sine of k pi over 2, right? That would work. But cosine k pi, I see it around, and you should be seeing it on your homework online. So if you see cosine k pi, know that that's this, and you have to use it. Cool. Time for us to do a problem. Let's say you have a summation of -1 to the k, 2 to the k, from 1 to infinity. I'm just going to put over here, or summation 1 to infinity -2 to the k. Do we all see this basic algebra? Do we all see it? Because most likely on your homework, this is the way it's going to show up. You should be able to split it and make this. We are all seeing this 6th grade thing, right? Good. All right. So this is our problem. Remember the procedure. Memorize this tree, draw it on your sheet somewhere, on a side, on a back, whatever. We isolate AK, which is 2 to the K, and we show that it's decreasing. Nope. We show that the limit K goes to, I mean, we're already done, but you show that the limit of 2 to the K is equal to 0. Nope. So diverges. We're done, right? I mean, divergence test kills this right away. So this is one of those divergent problems, and both conditions failed, right? Both conditions failed. Therefore, it's on the divergent side. We're done with this problem. Exactly. Let's take a look at summation of -1 to the k plus 1 over k factorial from 1 to infinity. How's this going to work out, right? All right. AK is clearly 1 over k factorial. That's it. You are taking off the alternating piece. So we have that. And now you're looking at this AK 1 over k factorial, and you ask yourself, is this decreasing? Is it decreasing? Yeah. Because what is the sequence? It's 1 over 1, and then what's the next number? 1 over 2, and then what's next one? 1 over 6. Good. What's next one? Times 4, 24. See how the numbers are becoming smaller and smaller as the denominator grows? So it's decreasing? Hell yes, right? How's the limit looking? Look at the sequence. Where's the limit going as k goes to infinity? Goes to 0. So yes, it passed both, right? So we are entering the convergent track. We have to figure out which convergence is it, right? But we are entering the convergence track. So now it's going to be either absolutely convergent or conditionally convergent. Let's see. So once we have this, we are entering convergence track. Now I need to test summation 1 over k factorial from 1 to infinity. What does this do? Does it converge? Does it diverge? Which test out of 9 tests? Ratio test. I have to use ratio test. So must use ratio test. So now I have a ratio test here. We know that it's the limit 1 over k plus 1 factorial times k factorial over 1 if I flip immediately. Don't forget the absolute values. It's extremely important to have those absolute values there. This is going to be a limit k goes to infinity, and then I have 1 over k plus 1 k factorial times k factorial over, I shouldn't be writing over 1, but these guys die, and clearly the limit is equal to, very good, 0. That's less than 1. 0 is less than 1, implies convergence. So now, answer. Since AK is decreasing and limit AK as k goes to infinity is 0, and summation of 1 over k factorial converges, the series summation negative 1 to the k, whatever I had, plus minus 1 over k factorial converges, oh sorry, absolute convergence. Converges absolutely. So whether you put C, A, C, whatever you put. We listed all of the conditions that we encountered along the way to get to absolute convergence. So I have AK was decreasing, the limit was 0, that pushed us into convergence track, and then on top of that we had that the summation of AK was convergent. So when all of those, right, you pick the branch that takes you all the way to absolute convergence. Yes, ma'am?
The only thing that negative 1 to the k tells you is that you're using alternating.
Yes.
So, okay, then the AK just, that's their test.
Yeah, everything, yes. So sequence AK pushes you into divergence or convergent track, and then series of AK tells you which convergence you get to pick.
What was that last part? Series
Which convergence you get to pick. So sequence, right? If you just have AK, that's a sequence,
yes.
right? And you are checking the sequence to be going to 0 and to be decreasing, right? You have that.
Yes.
And once you have those two conditions passed, you are on convergence track. Convergence track now splits into conditional and absolute convergence, and that convergence depends on whether the summation of AK converges or diverges. That's so the tree will always look like this. You start, it branches off into divergence or convergence, and then it branches off into conditional or absolute. That's how the tree looks like, and then you just fill in along the way conditions that various things have to fulfill to get you into any of these possibilities. Bueno? Great. Next example. Next example says summation of negative 1 to the k over k. What do we know about 1 over k?
Oh, that's divergence.
Yeah, what's the name?
It's harmonic.
Harmonic series and diverges, right?
Yeah.
All right. Let's write it out. So we are talking about AK, which is 1 over k. So what's happening with my conditions? Is it decreasing?
Yeah.
Yes, it's decreasing, right? And how is its limit?
It goes to 0. So you have to converges, and then you have to go to alternating or convergent, and since it's divergent, it's CC, the conditional convergence.
Just solve it by looking at it. That's it. This series converges conditionally. Under which condition? Under condition that minus 1 to the k is there. If it's not there, it's harmonic series in divergence. If minus 1 to the k is there, it converges. It's awesome. This is how awesome this stuff is. All right, so since this is yes and yes, it passed both of these conditions. We are on convergence track. So now we check summation of 1 over k, which diverges by p series or integral test, whatever.
You can't say like harmonic.
You can also say harmonic, yeah, because we are actually memorizing that one. You really don't want to do the proof on integral test on 1 over k every time you need it, right? It's one of the most frequent ones, so just memorize it. So summation 1 over k diverges by p series. So now we write the answer. Since AK is decreasing and limit AK is 0, and summation 1 over k diverges, the series negative 1 to the k over k converges conditionally. So you see that I put this capital N, right, to separate the two portions of the problem. The first one was testing only the sequence AK for decrease in limit, and that pushes us onto divergence or convergence track, right? So since it passed the convergence track, then I have the and now I have to see whether the series AK converges or diverges. In this case, it was divergent, therefore on a convergence track, but it diverged on a series, conditional convergence. This is the example that shows exactly that. Because, oh, the graph? Yeah, because remember how this, okay, this is an excellent question. Can you look at the graph and say whether this is going to converge or diverge? And the answer to that is absolutely no. Because in general, you cannot make conclusions about convergence or divergence of the series looking at the sequence. You cannot graph series. Series is just a value. Series is 1 plus 2 plus 3, right? Series of n. What is a series of n? What is this? This is 1 plus 2 plus 3 plus 4 plus 5 plus 6. And if you have infinity over here, it's going to keep adding forever. There is no graphing this. There's no graphing. What's a series of 1 over n? It's going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. And if it goes to infinity, it goes plus forever. There is no graph for that. There is a graph for 1 over n only. 1 over n does have a graph. So if I go just 1 over n without the sum, what you are getting is 1 comma 1/2 comma 1/3 comma 1/4, which is what I can graph. If this is 1 and this is 1, 2, 3 and so on, I get to graph 1, and then I get to graph half, and then a third, and then a quarter, right? So I can graph a sequence, and a sequence is going to be the sequence of dots. The series is the sum of a sequence, and if it adds to 3, then the graph for it is just this. 3, right? It's just a dot on the plane. So we cannot look at the graph and determine. More so that the 1 over n is this one, right? And negative 1 to the n over n is this one, right? So both of them look like, both of these are convergent sequences. But this is a divergent series, and this is conditional convergent series as a series. So this is why I say that the sooner you let go of the common sense, kind of try to push away from it, right? Learn the rules, right? Learn the rules. And then just obey the rules, and you'll be fine, right? That's technically what it is. Excellent question, thank you. Perfect. So big difference between sequences and series, right? Sequence you can graph, series you can't, because it just adds to infinity if it diverges, or it adds 7 if it converges, but then it's just that, 7. That's what it is. The whole thing equal to 7. Or pi squared over 2, or whatever else. Cool? Let's pick one example from the textbook. We already did 3. Let's do one more and then hit the break. And then chapter 9 after that. By the way, this is the last section in the chapter 8, and the chart that I distributed, I said that one is in the book. This is how the chart from the book that you have as official book looks like. They don't have telescoping series on it. I don't know why. Geometric and then divergence and all the other ones are there. And alternating is also on the bottom. So just different order. You have the same, right? How it look like, condition for convergence, divergence, and the comments at the end. And look, I love that they didn't just leave it blank. They say it does not apply. So maybe you fill that in or whatever on your sheet, right, that I gave you. Does not apply in the empty box for the first test, the nth term test. If you haven't changed the name, just add divergence test. It does not apply in that case because you shouldn't be showing convergence with a divergence test, right? No one is fat because it's skinny, you know what I mean? So there we go. All right, cool. Let's take a look at one of the textbook examples and look at the plethora of problems there. So we have 18 examples, and obviously all of them have -1 to the k, occasional k plus 1 or so. If you learn how to filter that little piece, and you also remember that when it gets to doing the series part, any of the 9 previous tests you learned applies, you're technically done with it, right? You know the tree, the way it branches, and then you just go one by one. Use your finger, cover this. Oh, 1 over k diverges because all of this converges, conditional convergence. I cover that. That's k over k, right? That's 1 there by the nth term test diverges, conditional convergence again. And so on. Right? So you just go down the line. And, oh, actually, sorry, no, this diverges, right? Diverges because of the doesn't test the condition, right? Limit is not 0, limit is 1/3. Sorry. Limit is 1/3, so diverges immediately. So just go down the list, right? P series over here, convergence, absolute convergence, and so on. All of them, like this. There it is, 22. Do we all see 22? Cosine pi k over k squared, right? Absolute convergence immediately because k squared, right? That's the P series, so it will converge on that second step. And yeah. So let's see, which one should we pick one? Any one of these. Give me a number.
22.
Okay, let's do 22 and 23 then.
Oh, wow.
Why? It's Thanksgiving, it's coming up.
I'm so excited.
So 22, it says summation cosine k pi over k squared. We start at 1, go to infinity. Ooh. Switch. So isolate ak, which is 1 over k squared. And then is it decreasing? Yes, right? Is the limit ak equal to 0? Yes. So we are on a divergence track, convergence track. So now we look at the series 1 over k squared, which is convergent by P series. Bueno? P is equal to 2, bigger than 1.
Yeah.
So convergence by P series, and then you just write answer. Since 1 over k squared is decreasing, and limit 1 over k squared as k goes to infinity is equal to 0, and summation 1 over k squared converges the series summation cosine k pi over k squared absolutely converges by alternating series test. That's problem 22. And then you asked for 23 because it looks really busy. Absolute conditional convergence just by looking at it.
I couldn't see it.
It's okay, you're gonna see it now. Once you learn this, you get to figure out which parts of the problem to ignore and which parts to focus on. This looks very busy. It says k to the 10th plus 2k to the 5 plus 1 divided by k times k to the 10th plus 1 from 1 to infinity. It's 1 over k. And we know the series of 1 over k diverges, right? So, conditional convergence right off the bat.
How is it 1 over k?
Because k to the 10, k to the 10,
Oh.
right?
Yeah.
So there is a k there extra on the bottom, right? So what do? We immediately isolate ak, which is this k to the 10 plus 2k to the 5 plus 1. And you quickly learn how to ignore the k to 2k to the 5 plus 1 part, because k to the 10 is the boss. So you have all of this. Is it decreasing? Clearly yes, because denominator is larger, and as denominator grows, the number gets smaller every time, right? Overall number. So clearly decreasing. And is the limit equal to 0? Clearly yes, again, because denominator is to the 11th power and the numerator is on the 10th. So denominator grows faster. It's going to drag it to 0. So we got the convergence path already. And now you use the comparison test, right, to 1 over k. So now to do the summation of k to the 10 plus 2k to the 5 plus 1 divided by k and then k to the 10th plus 1, we compare it to summation 1 over k, which diverges. So answer. Since AK, I don't want to write all of that, since AK is decreasing and limit AK is equal to 0 as k goes to infinity, and here's the capital N, summation AK diverges, the series, and now we have to write it, summation negative 1 to the k plus 1, and then k to the 10th plus 2k to the 5, kill me now, plus 1, divided by k over k to the 10th plus 1, converges conditionally. I forgot my name. I gotta practice. Copying this. Yes.
You know what I find annoying about all this is that, like, when you have two convergence, or like two C's, it's absolute convergence, but you know what I'm saying? How the answer you write CC.
Yeah, conditional convergence.
The other way around, if you have like two Z's, it would be, you know what I'm trying to say?
Yeah, you want to be convergence, like a convergence squared. Yeah.
two C's would be AC, and then a C and a D is DC. That making sense? To your tree. Like,
Well,
you
no,
know,
I just picked up the front coefficient. Spell it out if it's easier.
and I'm just saying, I wasn't the other way around.
Certainly.
Certainly convergent. Wow.
Yeah.
You are just 100% certain convergence. 100% certain convergence. Wow. All right. Sounds good. That's it. Chapter 8 done. Accomplished. Stream off.